Ladies and gentlemen, we are beginning our final approach into the end of the course. Please ensure your seatbelts are fastened and tray tables are stowed away. Landing gear down, flaps set to 30 degrees. We are on the final approach. During this lecture, we will begin to look at data processing as a means to solve a series of intriguing puzzles. Celebrate small victories and discoveries, turning data into a game of curiosity and exploration. Welcome again to another fun lecture of maintenance modeling and analysis. In previous lectures, we have discussed the application of supervised as well as unsupervised models to data. But how do we pre-process this data before we even apply the models? This question will be addressed in this lecture. Datasets in predictive maintenance are influenced by several factors that can compromise the integrity of the data. One such factor is noise. Noise can arise from diverse sources such as the malfunction of a sensor, environmental disturbances, or even transmission errors. Noise can obscure genuine patterns and trends, making it challenging to discern actual degradation from random fluctuations. Also, missing values. Gaps in data can occur due to reasons such as sensor failure, communication lapses, or even data entry errors by humans. Missing values can distort analysis and lead to incomplete or biased results. Inconsistent data. This includes discrepancies in data formats, units, or scales across different sources or even time periods. Such inconsistencies can lead to misleading analysis if they are not well addressed. For example, if you have dates in different formats in the same column, this can lead to problems dealing with the data. Superfluous data. Sometimes the datasets contain irrelevant information about the problem. This extraneous data can clutter the analysis, making it harder to analyze meaningful insights. Sometimes the high volume of sensor data in predictive maintenance comes from the comprehensive monitoring of machinery condition. Due to using various sensors and high sampling rates, we can now obtain terabytes of information per flight. While having a lot of data can be beneficial, it can also be overwhelming. Large datasets require more storage and also computational power. They can also lead to an increase of the complexity of the modeling process. In maintenance datasets, actual failure events might be rare compared to the baseline operational data, to the sensor data. This class imbalance can make it difficult for models to predict failures accurately. So if you have terabytes of sensor data, but you only have 3 failures, that can make your life a little bit more difficult. Large number of features. Datasets with many features or variables can introduce the curse of dimensionality, where models struggle to find meaningful relationships in the data. The importance of addressing these challenges cannot be overstated. Low-quality data, contaminated by the issues mentioned previously, will invariably lead to poor modeling performance. Hence, data preprocessing is an essential step to ensure optimal data-driven decisions. Let us see some of these problems in more detail. Noise in the context of data in signal processing refers to random, or let's say unpredictable fluctuations that interfere with the true signal or the true information. It can arise from diverse sources such as measurement errors, transmission disturbances, or environmental interference. And importantly, it can obscure or even distort the actual data, that is, the message being conveyed. In terms of noise, in predictive maintenance, sensor measurements are not immune to noise, which means that sensor readings can include errors that do not accurately represent true values. Addressing this issue involves, for example, improving the sensors itself, implementing filtering techniques of noise, and ensuring robust data collection practices. In here we illustrate the relationship between a signal and noise. The image consists of different television screens, each showing a different level of static, noise, and signal. The term signal refers here to the actual meaningful information or the pattern that you try to detect or to understand. The top left TV represents a dataset with a lot of irrelevant or random information where the actual useful data, the signal, is hidden within the noise. The bottom left TV is another example of noise where distinguishing the signal is slightly better, but very difficult. The top right TV illustrates a situation where noise is present but not overwhelming. The true signal can be detected, but it's still somewhat distorted by noise. The lower right TV displays a clear image with minimal noise representing low static and high clarity. The signal is easily identifiable and also interpretable in this case. Sometimes we talk about the signal to noise ratio. And then when we talk about it, we are discussing the strength of the meaningful information that is the signal relative to the background noise. A high signal to noise ratio means that the signal is much stronger than the noise, making it easier to detect or to analyze. In contrast, a low signal to noise ratio means that the noise level is high relative to the signal, making the signal harder to discern. In many tasks in maintenance, we need to enhance the signal while reducing the noise to enable more accurate predictions or decisions. Now let's talk about some noise reduction techniques, and let's start by the moving average or any other statistical methods. The moving average in particular, that we have already talked about in the lecture on forecasting, involves taking the average of a signal over some time. By averaging the signal, the noise, the random fluctuations tend to cancel out, enhancing the underlying true signal. The moving average filter, as suggested by its name, functions by computing the average of several data points from the input signal to generate each corresponding point in the output signal. Expressed mathematically, this can be represented as this equation. In this equation, x is the input signal, y is the output signal, and m is the number of points used in the moving average. This equation in particular only uses points on one side of the output sample being calculated. As an alternative, the group of points from the input signal can be chosen symmetrically around the output point, and in this case we are doing more smoothing than forecasting. Now let us talk about frequency domain filtering. Transforming a signal into the frequency domain using, for example, the Fourier transform allows the separation of signal components based on their frequencies. Noise, especially high-frequency noise, can be isolated and removed before transforming the signal back to the time domain. Wavelet denoising is another cool and interesting technique that you can use to remove noise. It involves decomposing a signal into wavelet components. This technique can effectively separate the noise from the signal, allowing a selective elimination of the noise components, of the components that are noise. In conclusion, the choice of the noise reduction technique often depends on the nature of the data, its type, and the specific application. Regardless of the methods that you select, the goal is always the same: to enhance the quality of the data, or let's say it of the signal, making it more suitable to perform further analysis or processing. When we are working with real-world data, it is common to encounter missing values. In your assignment, you will not see this in particular, but there can be different examples of missing data in the context of maintenance. For example, in this plot, we have the x-axis representing time and the y-axis representing the data of different flights. Each point in the scatter plot represents a specific measurement taken in a single flight. And here you see that the red points represent missing data. Missing flight data, such as the ones that you saw, can produce erroneous estimates of the remaining useful life if these are calculated in number of flights in cycles. When flight cycles are not accurately recorded or when they are omitted, predictive models can be severely compromised. In this other plot, we show events of failures of an equipment, a given equipment, and the failures in red are missing. And as demonstrated, the omission of even one data point, whether due to mislabeling or to human error, can skew the calculation of the time between failures, subsequently affecting the estimation of the remaining useful life. In general, missing data can be broadly categorized into three types based on the nature and the pattern of missingness. The type of missing data determines the appropriate method for handling the missing values. We illustrate the three types. The first type is missing completely at random, MCAR. Data is MCAR when the probability of missingness is the same for all observations and is unrelated to any observed or unobserved data. It means that the missing data mechanism, the mechanism behind the data that is missing, isn't systematic. It doesn't introduce bias in estimates, but it can of course reduce statistical predictive power. For example, in equipment maintenance records, if some data entries are missing due to random system glitches, then the data can be considered MCAR. Missing at random, MAR. Data is MAR when the missingness can be explained by other observed data, other variables. The gap can be adjusted if the relationship between the missingness and the observed data is correctly modeled. For example, in maintenance records, if technicians forget to log maintenance activities performed during night shifts, then we know that the missingness is related to the observed shift time, and then we can consider that the missing data is MAR. And finally, we have the third type of missing data, which is missing not at random. And the data is missing not at random when the missingness is related to the missing data, to the data itself, even after accounting for other observed data. Let me try to explain this with an example. A temperature may be more prone to missing data when the temperature itself is higher. So it has a relation, the missing data has a relationship with itself, with the feature itself. So let us talk a little bit how we can mitigate this problem of missing data. And one such thing is to input missing data. And it's the process, essentially, of substituting the missing values in the data with values that are estimated, that we believe they are more or less right. The primary objective here is to create a new data set that retains the original data without missing data, the statistical properties of this data. The choice of the imputation method should be informed by the nature of the missingness, of course, and by the specific characteristics of your data. So let's talk a little bit about the mean imputation, or the median, or the mode imputation. In this kind of imputation, you replace the missing values with the mean for continuous data, with the median, or eventually with the mode of the observed values. Let me try to explain this with a use case. Mean imputation can be suitable for data missing completely at random when the percentage of data that is missing is relatively low, So we have representative data to calculate the mean, the mode, or the median. But we can also resort to linear regression imputation, and then we use linear regression models to predict first, and then to substitute to replace missing values based on other observed variables. And this is suitable for data with linear relationships between the variables. Another method that I would like to talk about is the k-nearest neighbors imputation. Here, we replace the missing values by borrowing, let's call it like that, information from similar data points. K-nearest neighbors imputation is very suitable for data where relationships between the variables are nonlinear. We then have perhaps the most complex imputation method, that is the multiple imputation. Here we generate not just one dataset, but several, each with a different technique. We analyze each dataset separately, and then we pool the results to get the final estimate by, for example, averaging the missing data values that we have estimated in the different scenarios. This is suitable for example, for more complex missing data scenarios, especially when the data is not missing completely at random. Let me just clarify something. Although imputation can help produce a complete dataset, it is important to recognize, to know, that input values are estimates and not real observations. The imputation methods should then be chosen wisely. Understanding how the missingness works, why it triggered missingness, and in which way, can help select the most appropriate imputation methods. Despite the methods to mitigate missing data, there are several, it is always best to prevent missing data from occurring in the first place. An approach is, for example, through sensor design by selecting better sensors to minimize data gaps. Another strategy is sensor redundancy. In addition, understanding the sensors, their tolerances, their uncertainties, is also important. So we need to know the limitations and the accuracy of each sensor to anticipate and address potential issues. Finally, feature selection can also help us focus on the most important data, thereby reducing the risk of missing important information. Now that we are on feature selection, let's talk about the several advantages that it brings to the machine learning process. Usually in feature selection, we select the most relevant features so that the models can be trained more efficiently and eventually they can achieve better performance on data that is unseen, on the testing data. Reducing the number of features can sometimes lead to better models, let's say, but not always. However, in general, models with fewer features are typically easier to understand, to interpret, and this is especially valuable in applications where model interpretability is essential, like aviation. Formally, feature selection is a search problem for a concrete subset of features. Let's say you have a dataset of m features. Then we have the possibilities of 2 elevated to m datasets, including the empty set. There are several strategies to perform feature selection, including filter methods, wrappers, and embedded methods. Let's see each one of them in detail. Filter methods are generic and do not incorporate a machine learning model. They work by ranking features based on statistical measures, and they select the top ranking ones. Examples include, for example, when we analyze correlation coefficients such as the Pearson correlation, the chi-square tests, or even mutual information. And then we have the wrapper methods. These other methods evaluate subsets of variables which most contribute to the predictive model. So the predictive model is here used to assess if the features are good or not. Conversely, to filter methods, they are, like I said, based on a machine learning model. Common algorithms include forward selection, backward elimination, and recursive feature elimination. Let us now talk about embedded methods. Embedded methods are machine learning models that have built-in feature selection methods, so they do it inside while they are training. For instance, lasso and decision trees, random forests, inherently perform feature selection during model training, and this can be quite useful for us because we don't have to do feature selection separately. We can just do it inside the model. And let's now talk about dimensionality reduction. And what is it? It's essentially the process of transforming the high dimensional data, the data with many dimensions, with many features, into a lower dimensional form. And in this process we preserve, or we try to preserve, as much of the relevant information as possible. This transformation that we do, that we call dimensionality reduction, the goal here is to address the challenges and the inefficiencies associated with high dimensional datasets. One of the primary motivations for dimensionality reduction is to mitigate the effects of the curse of dimensionality, which can limit the performance of machine learning algorithms when they deal with a high number of features. Additionally, it's important to know that reducing the dimensionality can lead to decreased computational costs also, because you don't have so many features and you don't have to have so many storage requirements. Let us now talk about data quality and maintenance. And there are some metrics that are very specific to maintenance that we use in other fields, but mostly in maintenance. And they are the monotonicity, the trendability, and the prognosability. And they are very important to attain effective time series analysis. So whenever we have a data set, perhaps the first thing that we do is to check the monotonicity, the trendability, and the prognosability. The monotonicity provides information about the consistent, how much the degradation is consistent, how much it is moving always upward or always downward. Trendability and prognosability are important for modeling and predicting future system states. So let's start by talking about monotonicity. Monotonicity refers to the property of a function to be either consistently increasing or consistently decreasing without any reversals. And this has a lot to do with degradation, because as you know, degradation is typically, not always, but typically irreversible. So if you have a monotonically increasing or decreasing trend, this might help you better capture the underlying degradation. So you have here the equations that dictate when a function is monotonically increasing or monotonically decreasing. Trendability refers to the ability to always have the same trend for different units, for different equipments, for different engines, for example, if you are analyzing engines. So if you always have an increasing trend in all units, you can say that the system is trendable. While monotonicity cares only about one system, trendability looks at several systems. So in essence, we talked about different things today, such as denoising, missing data, data quality, very important, how we can do feature selection, how from a set of features we can just select the most important ones. We also talked about dimensionality reduction, not in much detail, but we talked about it. And importantly, I hope that you have grasped the idea that if you don't have a good data processing, it's very unlikely that you will have good models. So this is the end of the course. I would like to thank you all for watching the videos, for staying with us, and for enjoying the course as a whole. Thank you so much, and see you in the next flight.
On behalf of the flight crew, thank you for flying with us, and have a pleasant day.